Okay, so let's move on to the fundamentals. Before we go into too much, you should have done a course in your year 3 dealing with experimental aspects. So this course is mostly theoretical, based on what you have learned or happen to do. I can't remember the title of that course. I think it's HM334, something like that. So based on some experimental topics that you have done, of course, that you have done in other years. Even though we're saying it's theoretical, it doesn't mean that everything will only be derivations, and it will still include reasoning on your part as well. Okay, so the basic things that almost all forms of spectroscopy talks about is what we are talking about in this our fundamentals, which is we know that any form of spectroscopy uses radiation. You deal with energy levels that are present, so those are the theoretical parts, and then you consider the kind of interactions or the transitions that are taking place. Something that is very, very key is the intensity and why lines are not very straight. Okay, so let's move on into our topic for discussion today. So there's a picture in the background, clearer in some areas than in the others, which is something that you're familiar with. So that's an example of an IR spectrum, and the molecule is kind of represented there. So the idea behind it is, how do we go from that structure to that diagram and to the interpretation? That's the basis of what molecular spectroscopy, or in general, spectroscopy is all about. What leads to that picture and or whatnot. So let's start with basic definitions. Spectroscopy involves the study of the interaction of radiation with matter. So you're looking at interaction of radiation with matter. Matter, anything that has mass and can occupy space, is fundamentally built on electrons. So matter absorbs light. After it absorbs it, it can emit it. In other ways, it can also scatter radiation. So when it interacts with radiation, it can be used to quantify the amount of substance of the matter that you're interested in. You can use it to quantify it. You can identify some other unknown compounds, depending on what type of spectroscopy you are looking at. So these are things that are familiar with you. Then you can also use it to determine the molecular structure and nature of the bonds that are present in the molecule. So going back to this, once you're familiar with something, you can identify that, okay, there's an OH stretch and then there's a CO bond or C double bond present in the molecule. So we can go further into identifying the exact relative positions of each one to the other. Some other thing, you can also evaluate molecular properties, such as their dipole moments, how viscous they are, and all these things are used in design of new materials. The in thing nowadays is to research and design new materials for whether it's for drugs, for any whatever purpose that you might want to use it for. So I said that matter is the building block of matter is electron. It's not energy. So the other part of it, why we are interested, not necessarily, but the molecular structure, which is the matter that we are looking at, is in here, is the spatial arrangement of how atoms are arranged in a particular molecule, which is what we are interested in knowing. So molecular spectroscopy, we can say, is a means of probing the different molecular energy levels by interacting it with radiation. by shining radiation onto it. This leads us to the basic principle behind molecular spectroscopy in general, is that when you have a sample and then you shine light on it, for those of us that enjoyed our childhood, you remember that if you shine light on any prism or something, you see different colors. Now you can, if you go further, you would see more other things. So when you shine electromagnetic radiation of appropriate frequency, it interacts with molecules, causing some form of absorption or emission, or causing causing some form of transition between what we call quantized molecular energy levels. So the transition can be as a result of absorption of the radiation, in which case you absorb the light, or the molecule has already absorbed it, and in which case you are studying its emission. Energy levels present in molecules are often represented by lines. That's not how they are in molecules, but that's the way we try to picture it in real life. Each molecule has different kinds of energy levels, and we will discuss each one as we move along. So energy levels, those are the allowed energies. So let's see. Energy levels are allowed energies that a molecule can have. They are often represented by lines again, and then we continue all along. So we can call this the lowest one, maybe giving it 1, 2, 3, and so on and so forth. So it can be an electronic energy level, vibrational or rotational. Now, if the radiation matches the difference between that, there will be an absorption. That is the fundamental principle of spectroscopy. So we have mentioned radiation now. We have mentioned energy levels. Like with everything that we do in life, so we now need to go into more detail into what all these terms that are coming up, what they mean. Okay, my slide is not all right. So what is electromagnetic radiation? That is what is interacting with matter. By default, radiation is generally energy transmitted through space. So the energy can be transmitted as particles, or it can be transmitted as waves. In the field of theoretical physics, theoretical sciences, so those are the major types of things that we have in. We have the particulates and the wave nature of things. There are some things that are pure energy. So the particles are things like the alpha particles, beta particles that you learned earlier in your knowledge of science. But the one that we're interested in, the particles, you can still interact them with matter to get whatever you're interested in. That's not the focus of this course. Electromagnetic radiation, on the other hand, is pure energy. It is self-propagating wave, whether in vacuum or in matter, meaning that it does not require any medium for propagation. When you see it, it can be in vacuum. So it can propagate anywhere as long as it is started. Now, so note that it's generated mostly by charges, but it is self-propagating. Once it starts self-propagates, it has both electric and a magnetic component to it. Where's my that's what I'm looking for. So this is like a cartoon way of representing electromagnetic radiation, meaning that it has the magnetic component represented by the purple and an electric component represented by the green color. I want to believe that's what we are seeing. And from, I don't know why this is showing like this here. It's supposed to be just an arrow. So this equation came from the study of electromagnetic waves from classical mechanics. One thing that I just want to point out there is that the form of propagation is a sine wave, and that's why we can see the sinusoidal displacement of waves there. Remember what the sine function looks like in from trigonometry, and it goes on like that. Same thing with the electric components. So they are both sine waves that go on in their propagation. Important qualities that matter to us in spectroscopy: the speed, these 7 fundamental characteristics. The speed of the electromagnetic wave, we said that it can, let me expand this a little bit. So we said that it can move in vacuum. So the speed varies from different, if you go into another medium. Now, the direction is also an important component, because once the direction changes, some properties also change. And there are some properties of the molecule that affect the direction. Now, the polarization is orientation of electric field. Same thing, the amplitude, that is how high it can be. Okay, so, come on. The polarization talks about the orientation of the electric field. We're not going to go into that, but from physics, it can be linear, circular, or elliptical. So I mentioned the amplitude now, that's the maximum field strength, and that is often related to intensity. It is also related to when we are talking about intensity. Another key theme, so the first key one, that's the speed. And a big key theme is the wavelength. That's the distance between two amplitudes. And the frequency, that's how much cycles you get in a second. Now, the frequency, the wavelength, and the speed are related by that equation, C equals to V lambda. Now, frequency is also related to the energy of the particle that we are going to look at in the next slide. Now, this is that we just looked at is the classical way of looking at electromagnetic radiation. And when we say the classical way of looking, so we're looking at classical mechanics talks about every day-to-day objects that we see around us, anything that we see around easily. So that's what classical mechanics or classical physics deals with. But from the quantum point of view, so quantum mechanics deals with what we call the subatomic particles. They don't exactly behave the way we other things be. It's not like you pick up an electron, you throw it up, and then it goes back down, following the law of gravity. Now, are we saying that it doesn't follow any classical law? No, it follows it only in certain limits. So that's the thing. So quantum mechanics deals with subatomic particles, that is very, very tiny infinitesimal particles. According to quantum mechanics, electromagnetic radiation behaves like small particles of energy or small packets of energies, and this is called photon. Each photon carries a certain amount of energy. Also, Okay, this one is not in the slide. Also, there's another thing according to quantum mechanics. There's another thing according to quantum mechanics is that when you're dealing with small particles, molecules, atoms, like that, only certain energy levels, only certain energies are allowed. So this is, I don't know why. So let me write this out. This is Hc over lambda. That's what's supposed to be there. Hc over lambda, where H is a Planck's constant, and I think the value is a 6.626 times 10 to minus 34. So the first thing, according to quantum mechanics, energy behaves like electromagnetic radiation behaves like small packets, and we call that packet photon. Each photon of radiation is related to the frequency and lambda by this equation. If you recall the relationship between our C, V, and lambda. So the other thing that is not on this slide is, according to quantum mechanics, for atoms, for small particles like atoms, only certain energy values are allowed or can be possessed by the particle. That is a result of the mathematical derivation of the almighty Schrödinger equation, where psi is the wave function. I want to believe I have this thing somewhere, but I'm not sure. Anyway, but I need us to put that at the back of our mind. So that is the relationship. That gives us the relationship between energy, frequency, and wavelength. Just to mention one other frequency value that is used, another unit used is called the wave numbers, and is given the symbol V with a squiggly sign on it. And like my other equations, it is showing in a different way, but we'll continue. So we have that relationship that is important to know. So there are several, the electromagnetic radiation has one speed, but it has several frequency values or wavelength values. So it ranges. This is frequency. Frequency starting from about 3 times 10 to 19 per second to 3 times 10 to 9 seconds per second. Sorry. So the wavelength is much less than 0.1 here and about 10 to 9 in a big one here. So generally, when you talk about a spectrum is an array of entities. It can be anything, but they're usually arranged in an increasing or decreasing order of a common property in the process. Electromagnetic radiation is made up of photons of different frequencies. So that's the key thing here. Electromagnetic radiation is made up of photons. Remember, photons are packets of energy. Photons of different frequency. Or if you prefer frequency or energy or wavelength, whichever one you want to choose. It's something that is common to all the photons, their frequency, their energy, their wave length. Now, this electromagnetic spectrum, now, I said a spectrum is an array of entities. So the electromagnetic spectrum is an array or a continuum of all the electromagnetic waves arranged according to their wavelength or frequency, or if you prefer, their energy, whichever one you want to pick it. So how are these grouped? It has been noted that the um the different energies or different frequencies interact with matter in a different way. So the electromagnetic spectrum has been classified based on the way each type of frequency regions interact with matter. For example, as we have noted here in our picture here, let me see if it will allow me to make it bigger without messing up again. So there's a certain frequency range which I've marked 3 times 10 to 9 to 3 times 10 to 12 per second. If you put a particle there, it leads to molecular rotation. Now, if you move on to higher frequency, it leads to vibrations of bonds. If you move on to higher frequency, you have excitation of electrons, those ones that are very loosely bound. And then if you continue, at least we know why you can now excite core electrons. And the moment you start exciting core electrons, you are probably changing going to several chemical reactions that you don't want to take place. So that explains why it is often not advised to stay long in X-rays. And then in the low energy region, it only excites the nuclear motions, nuclear spinning motion. So what we are saying here is that the region's electromagnetic radiation is separated into spectrum based on how they interact with matter. It's not like it's something that came from the skies or heavens. I says that that's how it's going to look like. Saying that, so let's consider the overlap between the IR and microwave region. It is possible that you have some IR closer to where you have the beginning of your microwave region, and then you have microwave closer to where the beginning of the IR region. So what we're saying is that these regions in which we have separated them may overlap, but the classification is based on the dominant physical processes that occur when radiation interacts with matter. So for example, at about 3.3 times 10 to 12 or 3 times 10 to 13, you can have both microwave rotation and bonding going on. But which one dominates? That's the one that will take place. Okay. Now, so that's one aspect of our fundamentals, which is the electromagnetic radiation and electromagnetic spectrum. The next key thing that we want to talk about will be molecular energy levels, then the transitions or the interactions that can occur between electromagnetic radiation and matter. So again, energy levels talk about energy values that a particle may possess. Like we said, quantum mechanics, after understanding the concept of particles, realize that your atom, let me put it this way, if you have You can calculate the energy of a moving ball, and you can get an array of energies, continuous energies, but it's not the same when you're dealing with atoms. So those energy values were said to be, which are only certain of them are allowed, are said to be discrete. Atoms. One other thing, those energy values are related to the motion that are present in the particle. I don't have much space here. That's why I don't want to use it too much. So atoms have, let's look at it. So an atom is just a single, let me go back to this slide real quick. I have more space here. So for example, an atom is just like a spherical object of a nucleus and of a nucleus surrounded by clouds of electrons that are either in, like it has been solved, in orbitals, maybe s, p, or d orbitals. So they are only orbiting that motion. So the allowed motions here will be the transition of an electron in atoms. Allowed motion will be transition of electron. Are we still together? Okay.
Yes, ma'am.
Okay. Transition of electron from one orbital to another orbital. And okay, let me even say that here now. So an orbital is an example of an energy level. Now, it's not the same for molecules. A molecule, a simple one, will be hydrogen atom. Hydrogen atom can move as a whole. We can have this bond stretching and then compressing, that's vibration. And then you can rotate it whether in a clockwise or anti-clockwise direction or against the board. So molecules have more motions than atoms. So we say that they possess different types of molecular motion. The ones that we have, a translational motion, that's movement in a straight line. You have a vibrational motion. So the example that is given here, so you can bend this, take that up, that's a bending motion. My network interconnection is unstable. Then there's something we call symmetric stretching. Let me see where, yes, symmetric stretching. I don't want to go into too much details. You'll talk about that when you do vibrational. And then we have rotational motion. So stretching, whether it's symmetric or not symmetric, it means stretching of the bond. So symmetric stretching, you are stretching these two bonds simultaneously and then compressing them. Then you can have rotational motion. So electronic motions is another one that we can have. We are not showing that here. So that's usually transition of electron from one level to another one. So a molecule's total energy comes from several types of motion, not just vibrational. So we can say that the total energy is electronic, vibrational, rotational, and translational. So I'm going to add that there are some other types of motion due to spin motion. So that one does not have something we can think about physical in terms of our everyday life. Well, maybe, but it's usually more difficult to. Now, so let's look at these motions. The electronic motion, that's jumping from one orbital to another orbital. An orbital is an allowed state. The vibrational motion and the rotational motion are quantized. So quantized means that only certain, there's a picture coming there, only certain energies are allowed. Translational motion for molecules is not quantized. But when we're dealing with crystals, it is quantized. It's not quantized because the space available for motion is too much compared to the dimensions of the molecule. Unlike in crystals, where the crystals are in solids, where the molecules are confined to move only certain distances, then in such places, translational motion become quantized. That is another thing with quantum mechanics. Quantum mechanics becomes more important when you're looking at space confinement. Bringing an example to our everyday life, the more you are told to stay in a certain place, the more you know that there are certain rules that you must follow. There's a chat. Long time ago, somebody said they can't hear me. Can you hear me now, Ahmed, Usman, Adeshagu? Okay, others can hear. One person can hear. Can you hear me?
Yes, ma'am, we can hear you.
All right, thank you. Moving on. The rotational energy, like we saw the other time, takes place in the microwave region. Rotational motion, sorry, takes place in the microwave region of the electromagnetic spectrum. Vibration of the bonds within a molecule takes place in the IR region. Electronic transition takes place in the UV. So we can take it all over to X-rays too, because that one excites core electron. Gamma rays excites nuclear excitations. Then, if we can look at this, so the energy in those regions are of this order that I highlighted here. So if we look critically, we can see that electronic energy levels, the electronic energies are much higher than the vibrational energies, which are in turn much higher than the rotational energies. Nuclear spin takes place in the radio region. Electron spin takes place in the microwave region. So the other types of motion that are present, that's why I included spin here the other time, is the spin motion. Now in chemistry, it is customary to always represent things in diagram just for conceptual understanding. So electronic energy levels are much higher, are much, let's put it this way, much more widely spaced. Because they are wider, you require lots of energy. So they are much widely spaced than vibrational modes, energy transitions, which are in turn much widely spaced than rotational modes. What does that mean? It means that within one electronic transition, while just one electronic transition is taking place, several vibrations can take place. Or while one vibrational is taking place, several rotations can take place. Long and short is that each electronic energy level has several vibrational energy levels within it, and each vibrational level has several rotational levels within it. And this is also part of the reason why there might be overlap in some regions of the spectrum. Before we go to molecular transition, let's quickly look at one concept of called Born-Oppenheimer approximation. So this concept tells us that we can study the different motions in a molecule independently of each other. How? If you remember that our big diagram, you have where so the rotational, vibrational, and all energies take place in certain regions of molecular kinetics. So this is an electronic state. Within an electronic state, you have vibrational states, and within a vibrational state, you have rotational state. Now, because they require different energy to occur, they also occur at different time scales. That means they require each motion, electronic motion, requires a different time to take place. Same thing from vibrational motion. So there's a table that I have given here. Electronic transition takes place very fast. Vibrational takes place slightly longer. Rotational takes place much longer. And then you have spin. So now we say that they occur at different time scale. Born-Oppenheimer approximation, which we'll quickly see the exact approximation on the next slide, says that because of this, there are different time scale, we can study the energy, says that three motions are independent of each other. So this is the total energy. The total energy can be represented as that. The implication is we can study this separately. We can study this motion separately. First, we can solve for electronic structure, then we can solve for vibrational structure, or then we can solve for rotational energy levels. Or we can do it vice versa. Long and short, because they occur in different time scale, the different motions that are present in molecules can be studied separately. So if you're looking at an instrument that is working in this time frame, you know that you can easily study rotational without considering electronic. What is Born-Oppenheimer approximation in itself? Born-Oppenheimer approximation came from when solving the motion, the electronic, while the structure or how electrons are arranged around a nucleus. Much after it was found out that the electrons are much, much lighter than the protons. So it says that because the nuclei in a molecule are much heavier and as such will move much more slowly than the electrons, the electronic motion can be treated as occurring in a fixed field of a stationary nuclei. Now, the truth of the matter is the nucleus is not stationary, but because it is heavier, you can quickly study the electronic structure, the motion of the electron, and then once it moves on, then you can see whether it has changed or it hasn't changed. So what it led to in its original definition is that the total molecular wave function can be expressed as motion of electron and motion of nucleus. A quick one about what is a wave function. You studied this a little bit in atomic spectroscopy. A wave function, that's a mathematical representation of a particle or of a system. We know what a system is from thermodynamics. Whatever you are interested in whatever you're interested in looking at, that's what a system is. So the mathematical representation of that system is what we call a wave function. It is said to contain all information about the system. And whatever you need to know about the system, you use what we call an appropriate operator to get out your information. So in an atom, you have an electron and then you have a nucleus. So you can separate their motion, and that's the basis of Born-Oppenheimer approximation. So they occur at different time scales. So the same reasoning was now applied to electronic motion and vibrational and rotational motion. So, what's the time? Okay, we still have some time. One thing, though, that we need to be aware of, which we will see when we're talking about individual spectroscopy, individual electronic rotational, is that even though, this is an approximation, just like the person giving the seminar topic said the other day, anytime you are writing a report, you need to remember the approximation that was considered. This is an approximation, which means it works in certain limits. Works in certain limits. And again, we mentioned it a little bit the previous time when we were talking about electromagnetic spectrum. There can be overlaps in some areas. So, although the motions are treated as independent, in practice, you can have coupling. Coupling, as in interaction, or more like overlap, that are taking place. So you can have vibronic coupling, that's interaction between vibrational and electronic state. Low vibrational, you can have interaction between rotational and vibrational motions. And then you can also have a coupling between the three. So you would only need to look at it when it is needed. When it is not needed, then you need to solve a small place, then you just focus on that short interval. So these couplings lead to what we call fine structure or splitting of lines. This splitting of lines is very, very crucial in NMR. The fine structure is crucial. You get it in NMR too, and you get it in vibrational spectroscopy. Even though it makes spectra I think I'm recording it. Unless it has stopped recording. Where is it? Even though it makes spectra. So Adeleke, I am recording the video. So even though it makes spectra more complex, but it gives more information. All right. So let's talk about the different modes of interaction that are present. An additional one is factoring. So we said we were talking about the energy levels and the different modes of transitions that can take place. So the three basic modes that are often discussed are the absorption, emission, and emission. So stimulated emission and spontaneous emission. So let's quickly go into them. Stimulated absorption or induced absorption, or simply, you can also just call it absorption, is just excitation of the molecule. So it is a radiative process that occurs, remember, that occurs when a photon with energy is absorbed. I remember the saying that energy levels are often represented by lines. So the molecule was initially in a lower energy level, and then it absorbs frequency. It absorbs photon. Photon is a packet of energy. In short, it is energy. The energy is equal to h V, Planck's constant, times frequency, making it to jump to a higher state. The energy difference between the two states that we are talking about must be equal to the energy of the photon. If the energy is not equal, then absorption does not occur. And we often represent the process as M being in the ground state going to excited state after absorption of photon. Net result is an increase in molecular energy because you have absorbed energy. This is the basis of any form of absorption spectroscopy. Experimentally, when you shine light and then some of them are absorbed, and when you are recording what is left, you will not see this frequency and you know that energy has been absorbed. What can happen after the energy is absorbed? It can relax back through any process, or it can be further absorbed if it has the right energy. The next one is the stimulated emission. Stimulated emission is also a radiative process. All three that we're talking about, they are radiative processes, meaning that they involve light, whether in absorption or in emission. So it is a process that occurs, excuse me, when an excited molecule is let's look at let's emphasize stimulated. So your molecule is already in an excited state. Our energy levels are represented by lines again. That's not what molecules look like, but that's the conceptual way that we can see it. So its process occurs when an excited molecule, M star, interacts with an incoming photon of a specific frequency and makes it go to a lower energy state, emitting another photon in the process. So the photon that is coming in must also match this energy difference. So it stimulates it to go down and force it to emit a photon. So which means one photon comes in and two photons goes out. Thus, so we say it is a two photon process. Since you're coming in as one and going in as two, there has been amplification. So we say it is a two photon process that leads to amplified. Then the last one, to amplified unidirectional coherent beam, meaning that the photon that's coming in, it has its direction in which it is coming from. So it emits another photon, and it is also in the same direction of that initial photon. So it is same energy, same phase, same polarization, same direction. So that is the thing about spontaneous motion. It results in a net decrease in molecular energy, and this amplified unidirectional is the basis of our laser operation. That's the one that we use to the common one that we see is the pointer that we see when people are making their presentation. That is an example of application of stimulated emission. We see that that's not the only place it's been used, but that's just one of the examples that I want to mention. So the third process is spontaneous emission. So we just looked at stimulated emission. Stimulated emission requires you to shine light initially or put in energy and then cause an excited molecule to go to a lower energy molecule. Spontaneous emission, on the other hand, your molecule is in the excited state, but it goes back to the ground state. Because it is going back to the ground state, it emits energy. Everything has to be balanced now. However, there is nothing causing it to emit, so that's why we say it is spontaneous. Now, that's a photon that you emit, since it's not being coerced into coming down, it can go in any direction. So the emitted, so you know that in a molecule, if one mole enough has how many particles? Has particles in billions. So you have random directions. There is no phase relationship between the photons that are emitted. They just come out just like that. So, excuse me, where do you see this? We see this in our lamps, most of the times that we put on lamps. So the particles are excited, and they spontaneously emit radiation in all directions. It results in net loss of energy similar to the stimulated emission that we just discussed. Of all the three processes, spontaneous emission is the most common of all the three processes. It's actually the one that's most thermodynamically will go. That's the direction of thermodynamics. You know, thermodynamics is always seeking to go to the lower energy. So that makes sense why it is the most common. Before we round up our class, we'll go on to discuss the last type of the other two types of interactions. So these interactions that we've talked about involved absorption of light, and after absorbing it, you can now emit it. However, remember that we said that one of the properties of radiation is a direction. So that's the direction of propagation. The direction can be changed, and when the direction changes, we say that light is being scattered. So scattering is the process in which light changes direction due to interaction with particles or molecules. So you're changing the direction rather than absorbing the light. So that's another mode of interaction. So we can have absorption, emission, or scattering. Now, so we say due to interaction with particles or molecules. So this other definition says upon encountering an obstacle or irregularities in matter. So there are some molecules that possess this ability to scatter light. Not all particles possess the ability to scatter light. The background picture is showing how the sun rays are being scattered. Anyway, how does this apply to spectroscopy? So that's this is the Raman. You can scatter the light at the same frequency. So light is coming at a certain frequency. So this is light coming. There's an absorption, and then there's an emission. But rather than it can be scattered. Now, so when you scatter it at the same frequency or wavelength, you call it an elastic scattering. No change. Electric scattering does not result in any change within the molecule. It does not give an insight into the energy level of the molecule, since it is being at the. But then the one that is very useful to us is the second one, the inelastic scattering. Inelastic, excuse me. Inelastic scattering means that the radiation that is coming was redirected, not just redirected, then the frequency is changed, or the wavelength is changed, or the energy is changed from the incident photon. So there's a way it's often represented. So this is light, that's the particle. This is light. It can be scattered at the same frequency. So this is angular. Oh, did I mention that? in one of the slides. Angular frequency. Angular frequency is related to the regular frequency by that formula. So you can have it at same frequency, which we call the elastic scattering or Rayleigh scattering. You can have it at the different frequency. That one is often called the Raman scattering. So once it's at a different frequency, it tells us that something has happened, something is about the molecule. There's something about the molecule that we need to understand further. So it gives insight into the nature of the molecule. It can be used to study all forms of energy levels, rotational, vibrational, or electronic. So much like absorption and emission are used to study them, the scattering can also be used to study them. The last interactions that are present are the magnetic interactions. So magnetic interactions, that's interactions that occur between particles with magnetic moments and an external magnetic field. So magnetic interactions, particles with magnetic moment, for example, a nail and a magnet. Electrons and nuclei, they have something that we call spin. It used to be said that spin is you have something that the nucleus moving at about its center, but there's still much research going on it. So we're just going to tell you that it is an intrinsic motion within the molecule, and it results in making it results in some form of generating magnetic moments. Why does it result in that? Magnetic moments are created by moving charged particle. The electron is charged, negatively charged, so its motion, its orbital motion also causes magnetism, but it's usually not focused upon. But then the nuclei too, it's positively charged, so its motion also generates magnetic fields. So once you generate simple magnetic fields like that, you act as magnetic dipole. When you place those inside an external magnetic field, what happens is that those spinning motion create what we call energy levels. And once you have those distinct energy levels, if you shine electromagnetic radiation, that is what electromagnetic radiation comes. It causes transition between the different spin states. So you can move from a spin down motion to a spin up motion. That's the conventional way of talking about spin. You call it a spin up and a spin down. Just to note again that there's still a whole lot of research on knowing the exact nature of spin, but all experiments so far that has been done in the past over 200 years shows that there is an intrinsic motion in the molecule. So it is the basis of ESR and NMR, both powerful methods in structural elucidation in medicinal field, in drug delivery, and in so much more. Okay. Any question? No. We're going to start with intensities of spectral lines and in our next class. That should be Monday. Monday or Tuesday. I will let you know. Then I will also let you know whether we'll have an online or physical class. All right. Any question? All of them. How many people are in class now? Let me say 65. Only 65. Minus 2 of me. That's 63.